And it's always interesting standing up making predictions and then looking back a couple of years later to see what came true and what didn't come true. And I looked at a number of key issues which are core to HPC, and these are still core to HPC today. In some areas we've made progress, in some areas we haven't, and so we will look at what we've done, where we've come, and then at the end I'll look at where we're going in these areas as well. So the areas that I picked were multi-core, GPUs, and I'll explain later why GPUs should be broadened out to accelerators generally, scalability, cloud, and software. And talking about software, it's specifically software development, programming methodologies, and so on. So back in 2010, multi-core was relatively new. Many people had 2 or maybe 4 core systems. We were looking towards 8 or 12 core, and hyper-threading doubled the potential parallelism within a single chip. And the forecasts that we discussed then were really looking at some of the experimental chips that were available. IBM had a chip called Cyclops that I think had 64 cores. Intel had a range of experimental chips with between sort of 48 and 80 cores. And the reason for building these experimental chips was to try out different things, to see where shared infrastructure within a chip was successful and where it wasn't, and to identify what should be done for building the production many core chips in later years. So where are we today? Well, Intel with their microprocessor, which is about to become reality, will have, they say, more than 50 cores. That should probably be pushed into the accelerator piece, and I'll talk a bit more about that later. So mainstream processors, AMD's Interlagos is 16 cores, which sometimes look like 8 depending on what you're doing. And the Intel Xeon E7 has 10 cores, and with hyper-threading that looks like 20. So we're sort of in the ballpark of where we expect it to be on mainstream multi-core processors. So back in 2010, NVIDIA was pushing to be the sort of the main vendor of GPUs for the HPC market. AMD with their ATI chips was also making an impact, but a smaller one. And FPGAs, although they're not GPUs, they kind of fit into the same accelerator piece. And they were being used in a number of niche areas, and the question there was, will they stay in niche areas, or is there an opportunity to do other things? So the forecasts that we put forward then were that HPC systems would have heterogeneous processors. The main reason for that is from a power consumption point of view. We'd reached a point where we couldn't keep building HPC systems as we had, and having heterogeneous processors with some of them able to deliver very high performance at relatively low power was a good way forward and a good way to address the power issue. And longer term, we forecast that GPUs and CPUs would indeed share the same die. So today, the 2 main accelerator processors around are NVIDIA GPUs and the soon-to-be-launched Intel Knights Corner. They've progressed pretty much as we expected. We don't yet have the GPU on the same die as the main CPU. And FPGAs are still there, particularly Maxillr and Convey are doing useful work with them, but FPGAs remain a niche within HPC. And there's much discussion and debate about multi-core and many-core. And whenever I talk to somebody who uses the term many-core, I ask them to describe what they mean. And the answer is usually, I know when I see it what it is, but I can't describe the difference between multi-core and many-core. The best description I've heard was during a briefing with PGI a couple of days ago, and their position was that multi-core is optimized for latency, whereas many-core is optimized for bandwidth. So if you're doing big sort of vector type of operations, then many core devices are right for that. But that still doesn't enable you to stick a label on something and say that's definitely multi-core, that's definitely many-core. But there will be a variety of different architectures that we will use in HPC going forwards. So one of the trends that concerns me deeply, both at the entry level and at the high end, is scalability. In the past, somebody who just programs a small server or a high-end desktop system didn't have to worry about parallelism. But we could see with the number of cores that were being added, and with even sort of mainstream workstations having GPUs, accelerators, the complexity of programming for Joe average programmer was increasing, and they had to become concerned about scalability, the number of cores in each processor, the number of sockets in their systems. Clusters were becoming more and more complex. The amount of kit you can get in a single rack is increasing, and then systems built out of multiple clusters, and grids built out of multiple systems. So at every dimension, there are issues with scalability that need to be addressed. And the two forecasts that we made at the entry level, we said that commodity SMP systems would soon exceed 100 cores, and at the high end, people were working towards exascale systems, which would have many more complex scalability issues. So where are we today? I just picked an HP system. I could have picked one from many vendors. This is a 4U system, and it has 80 cores. They're Intel processors, so with hyperthreading, that's 168 parallelism. So we're pretty much on target for having around 100 cores in a commodity system. And we're still some way away from exascale. There's a lot of good work going on in all geographies in the world, but we still have many more problems to solve. It's kind of funny to think that 2 years ago, cloud was something that we were just beginning with, and now it's become ubiquitous. So Amazon was certainly the main company that was banging the drum for cloud, but there were many other companies talking about migrating their offerings to cloud. And what we said about cloud and HPC 2 years ago was that HPC is all about optimizing your application. It's all about understanding the underlying platform and structuring your application in such a way that you can maximize the performance. Whereas cloud is all about virtualization and abstraction. It's about hiding that complexity from the user. So I said that there was going to be a significant problem in bringing these two ways of thinking together to enable people to run HPC applications in the cloud efficiently and effectively. So what we've seen is that a number of the cloud providers have started to deliver HPC-specific capabilities. So Amazon, for example, has tons and tons and tons of vanilla cloud, but then they've got some special HPC cloud, and also Penguin and SGI. What they're doing there is effectively they're building an HPC-tuned facility and wrapping a cloud business model around it. So it doesn't behave in exactly the same way as the cloud does. You may need advanced reservations if you want a particularly large capability. But it does bring together HPC and cloud, and it solves the issue that I talked about 2 years ago, which is that if you don't know what the hardware platform is going to look like, you can't optimize your application for it. Cycle computing does something slightly different, and that is that they provide a software infrastructure that enables people to run embarrassingly parallel applications on the vanilla cloud without worrying about the complexity of it. And they've run a number of jobs that have been using tens of thousands of cores on Amazon very, very successfully. So all of these wonderful systems with multiple cores, accelerators, massive scalability, possibly running in the cloud, are great, but unless you can program them, there's not much point to them. So we looked at the trends in terms of software development tools, and OpenMP and MPI are the kind of de facto way that people build their HPC applications. And 2 years ago, CUDA was still emerging, and there were a number of other programming models and languages that were being used. Our forecasts for software it wasn't so much a forecast as a panic. There are many problems that need to be solved and addressed. You know, as the hardware options become more complex and more varied, how do we write a program once and have it run on any of the different platforms, whether it's AMD multi-core, Intel multi-core, NVIDIA GPU, or Intel mic? And if we have to worry about each of these different architectures and tune our applications differently, then maybe it's just going to get too complex, and the fact that we have relatively low-cost HPC platforms won't matter, because programming them will be very, very expensive. Now, HPC for the masses is talking about the fact that with lower-cost HPC platforms, we have opportunities for people to do things they couldn't do before. So a single rack cluster for a few $100,000 has an amazing amount of compute power, and it enables people to do design work or design optimization that they couldn't have considered before. But they need to become an HPC expert to be able to do that. And even down at the single system level, where you're talking about 10, 20, soon maybe 50 cores in a single workstation, people have to become an HPC expert and able to be able to write their applications optimally for that. So we either need to educate the masses as to how to use HPC, or we need to provide tools and techniques that make that much more straightforward. And the evolution or revolution piece is sort of looking back to when OpenMP and MPI emerged. OpenMP would enable you to take a serial code and adapt it for shared memory parallelism. And you could do that in a piecemeal fashion, picking your sort of the hottest spots of your application to begin with, and then moving on to other areas. But when MPI came along, people had to almost throw away what they had and start again from scratch. So there was kind of a pause when MPI arrived in the scene. And the real question is, what are the programming models going to be that we use going forwards? And is it something that we can migrate to easily, or is it something where we need to stop, think, and have a pause while we re-architect our applications? And then whatever we do, we've got the cloud as well. What impact is that going to have on software? So in 2012, CUDA has become very well established. Intel, because they use the same tools on mic as they use on their x86, put that forward as being a very easy migration to make. And what we've seen over the last year or so is that the OpenAC, the effectively extensions to OpenMP for accelerator programming, is being worked on by a number of key vendors and compiler companies throughout the industry. So there's a very good opportunity that the OpenAC will become a way ahead of bringing together programming for architectures like Intel mic and NVIDIA GPUs and other platforms. Having said that, the idea of writing once and deploying anywhere, especially in a consistent, efficient manner, it's still a bit of a dream that the industry is working towards. So I've looked at the forecasts that we made across these trends back in 2010, where we are today. And now I'll make some forecasts about where we're going to be in a couple of years' time in these areas. So in mainstream x86, the number of cores will continue to grow slowly and steadily. There is tons of baggage and legacy that the x86 architecture has to bring with it. So to be able to double the number of cores sort of every couple of years or so is really quite remarkable. But to do that in a way that's efficient is becoming more and more difficult, but it will continue to happen. However, there are other platforms that will start to emerge, if not in the mainstream yet, at least for some niche areas. And so HP's system based on the Calxeda system using multi-core ARM chips specifically addresses the power consumption issues for some classes of enterprise or cloud use. And then, slightly more radically, companies like Adaptiva have designs for chips with up to, in this case, they've got a design for 4,000 very simple cores, which are focused on just doing tons of floating point arithmetic, but they don't have all of the infrastructure and the support that you maybe get on the x86. So different types of cores will impact different areas of the market over the next few years, and I think it's going to be a fascinating time. In terms of the accelerator market, the next year we're going to see an interesting battle between the Intel Knights family and NVIDIA's Kepler GPU. Intel, because it's Intel, will have many followers. The relative ease of moving applications from x86 to Intel Mic will be attractive to some. NVIDIA has the installed base and is currently the leader in terms of accelerated computing. So they both have very strong positions, and it's going to be interesting to see how it pans out. In the background, NVIDIA is working with ARM on a number of research projects, and we will certainly see what we talked about earlier, the CPU and GPU on the same chip. Indeed, that's already happening with Tegra, but that's not really mainstream HPC. But we will see that happening, I think, in the next 2 years. And FPGAs, I think, will begin to make more of an impact, not necessarily because they'll become easier to use, although I think there is some work going on in that space, but because of all of the other issues that I've talked about, scalability issues, the multi-core systems plus accelerators. At scale, these are becoming more and more difficult to use. So particularly for very, very large systems, possibly the complexity of mainstream HPC will begin to mirror the complexity of FPGA-based systems. And where there's a very good fit for your application with FPGAs, it is possible to deliver petascale or maybe even exascale performance within a relatively small system. I'm not pretending it's easy to do, and there's a great deal of work to program FPGAs efficiently. However, there are some classes of work, particularly if you're not just doing lots and lots of double precision floating point, where they can deliver very cost-effective performance. They are difficult to program, but as we start to look at larger and larger systems, I think it's an area where we will see FPGAs not breaking out of their niche, but at least their niche will expand. All of the scalability metrics that I talked about will continue to increase, and one of the interesting issues with regard to scalability is that the size of high-end HPC systems scales faster than Moore's law. So HPC isn't just riding the scalability that we're seeing at a component level or system level, but we're increasing that all the time. So I may be being slightly too bold to say that HPC in the cloud will reach maturity, but I think that we've made significant progress over the last 2 years, more progress than I'd anticipated. I think we'll see more cloud vendors providing HPC capabilities. We'll see more HPC facilities offering cloud business models. So I expect to see this increase. Another angle on it is delivering HPC applications as a service. One of the problems that has held that back in the past has been software licensing. Software licensing has always been an issue for people who want to adopt the newest technology, because the software vendors tend to want to make the most money out of running their applications on older technology. But there are a number of software vendors who are now taking a fairly liberated view in terms of delivering their application as a service, and you pay for what you get rather than having to buy expensive licenses that you may not use all the time. And one of the benefits of delivering HPC applications as a service is that it brings that capability to users who don't understand how to run an HPC facility. You know, a relatively small engineering firm may want to use some applications, but they don't want to build a a large cluster and run it and manage it and worry about how to make sure it's running efficiently. So delivering those things as a service from the cloud is going to give access to HPC to people who don't have it today. Now, in terms of software, we'll continue to see OpenMP, MPI, and CUDA being used very, very extensively. And from looking at how well OpenAC is being talked about and adopted within the industry, it looks as if that's going to be a good opportunity for a model to move to an open model of programming for accelerator systems, which will at least let you program once and run anywhere, although not necessarily efficiently without doing some tuning for different platforms. But the same is true for OpenMP as well. So that's looking at programming at sort of an entry level and mainstream HPC. Looking at Exascale, we still have a problem. There are many issues to be resolved. There's an organization in the States called the Exascale Report, which has been monitoring this debate. They recently did a survey, and within that survey they identified the single most difficult barrier to moving towards exascale systems. And I expected the answer to be something like power consumption, architecture complexity, or one of the issues we've discussed today, multi-core, scalability, and so on. The single most difficult barrier they identified was politics behind funding. So even if we solve all of these technical problems, we've still got other issues. This is a European conference, and I'm glad to say that at the moment, the European Commission seems to be doing a good job in terms of funding projects that are moving towards exascale. There's a series of PRACE projects that have been both supporting users and building systems, including what they call PRACE prototypes, which are sort of petascale type systems using innovative technologies. And there are a number of projects which are developing software moving us towards exascale, and at the same time building platforms which will enable us to exploit that. So in terms of software, we have some major problems in getting towards exascale. We are addressing some of them, but there is still work to be done, both in terms of the technology and in terms of the politics around funding. So 2 years ago, I ended with this quote, which is allegedly from Confucius, "May you live in interesting times." And the point about the quote is that it sounds as if it's a good thing. Isn't it nice living in interesting times? However, some people say that this is a curse, because if times are too interesting, they're too complex and you can't actually manage them. So we still don't know, in terms of HPC architecture and software, whether living in interesting times is a blessing or a curse, but it sure is fun. Thank you very much.
Any questions for John? John, would it be feasible to include the people aspect in your future forecast?
To add the people?
Yeah, what's happening with people? Engineers, skill. We have enough of these around. I mean, we're moving to exascale, and we haven't even got people to support cloud infrastructure, small infrastructure.
Yeah, so I think the people issue, that's a very good point. The people issue is two issues, really. One is, at the high end for exascale systems, the complexity is enormous, and we really need to have a range of skilled people supporting that. But also at the entry level, where multi-core, the average university, and this is true worldwide, does not teach parallel programming in computer science at a bachelor level. And given that an average server, a small server nowadays has 10, 20 cores, I think that's criminal. And so there's a great deal of training that we need to do to enable the programmers that we have to use the systems that we're going to have in the next few years. And there's another example that there was a project at a very large IT company which was targeting large parallel systems. Of that team of over 1,000 programmers, I think it was only 3 or 4 were actually allowed to do anything to do with parallelism. Now that means that 990 odd of them aren't aware that that bit of code they're writing today is actually going to have parallel implications, and that I find kind of scary. So I think there are major problems that we have both at the multi-core, low-level parallelism and exascale, where you're absolutely right that people are crucial and skills gap is large and growing.